Thank you. Hello, everybody. Today, I want to talk about a new paradigm. We want to do the computation which is related to digital twin. What I want to do is at first, I wanted to thank our team. We had extensive work over the last 1 or 2 years. This is where we arrived. This is our team, in particular this talk. I want to also acknowledge our Cosmic AI Institute to give us tremendous opportunity to implement your dreams. For all of the original architectures, you can see we wanted to understand the outstanding questions, the origin of the universe, but there are a lot of barriers. We have the observations, the real world, physical world. We also have this simulation with theoretical need, proof, or feedback. And astronomers are certainly the center of the universe. Luckily, we wanted to tackle this problem. This one single problem is how to reconstruct the early universe. And when we look at the whole space, the timeline of the universe, it goes back to 3.7 billion years. This is a long time. So this is a tremendously challenging task. And we know the skies and we know the stars and the galaxies we can see, but there's a lot of spaces in the dark, which is dark matters that play a crucial role. Today, I mainly want to talk about the computation challenges with this tremendous opportunity. A lot of cases, our simulation is composed in these high dimensional 3D grids. And it's computationally very challenging. Another side is that we have tremendous opportunities using statistic and machine learning models, but they cost like thousands of CPU hours for our training samples. This challenge is impose us to think about if we can do it differently. So this is to come up with the inverse problem. We want to, given the current observation of the universe today, and trace back to the initial conditions. However, this problem, the inverse problem, is ill-defined. In machine learning, we can predict, get a one single point answer. But how about we do it in a way, because of the nonlinear nature of gravity, we can have some uncertainty control. So we can have the prediction with uncertainty and with a multiple possibility and the distribution. So the whole goal here is trying to find the pathway, how we move forward with this challenging problem. One observation we had learned from this work is that the simulations generate a lot of the 3D space with empty vaults. This actually occupies tremendous part of this simulation. And that will cost billions of flops to process them, which is turned into the CPU hours, the time, and the cost, and all of this. But we really want to look at what exactly is the high resolution densities for the real materials, and including the visible ones and the invisible ones, including dark matter. With that, we have this observation. We see that the sparsity duality is the problem, and we have the spatial duality is uniformly distributed when we do computation or simulation. On the other hand, we have the wavelength domain, which be underused, but is highly adaptive to give us the real signal information. With that understanding, we want to do some experiments. We want to see how we can bridge this and transform to the new way of doing this inverse problem. So we use the cohortic simulations. As you know, they have a tremendous amount of n-body simulation, a lot of data, and we're currently handling gigabytes, terabytes, is going up to petabytes in the future. To prepare the data, we first need to convert the n-body simulation output to density field and transform that to over densities. And we started by this simulation and try to use a train by a baseline model. This baseline model uses the conditions, and we wanted to use present-day dark matters, the density field, which is starting from 0, go back to the early universe, is 127. So in this case, we'll come back to think about what the toolbox we have, what the methodologies we have. So there's an evolution of all this model from very early stage, like people might have heard about GAN and a variational encoder, and we latestly, last 2 or 3 years, and we switched to diffusion model, which is a big revolution. However, diffusion model has several drawbacks I will talk about shortly, and from there continue to improve. And we have a hierarchical transformation that continues towards the flow model. In the right-hand side, you can see there are simulation of forward simulation and the backward, which is the inverse problem we're talking about today. The baseline model is diffusion model. Has anybody heard about that? It's basically the idea is that we have a forward model, we gradually add noise and train the model to learn the noise, and then reverse engineer when you give input to the back of the distribution of data. That model is very well studied and used, and so we use that model for our training of this as baseline. What you see on the right-hand side, you can see the non-linear transport of the path bending. And that's very time-consuming because each of these steps is incremental. That is the barrier, one of the barriers of the diffusion model. On the left-hand side, you can see that we use that 128 as our dimension 3D cube, but that dimension could go up to 226 up to 1024. That will dramatically introduce more computation costs because n squared, n cubed. If you look at this output of the power spectrum and the cross-correlation transfer function, you can see use diffusion model, we had baseline. They did very well at the pixel base, especially matching the large structures. You can see the red is the outcome, and the dashed line was the ground truth. However, if you look at the right-hand side, there's a gap with a small structure, and it eventually cannot capture. So that's the second barrier of the pixel-based diffusion model. With these incentives, we're trying to find a better method to address these fundamental problems. So we look at different domains as wavelet, because spatial redundancy and the uniformly distribution was very inefficient. And the wavelength composition is more concentrated on these signals, and we can use the unit to learn the spatial relationship. At the same time, we transfer to the wavelength domain. And that is the essence of our methodology. What are the real problems here? In general, we want to use generative AI method to address this very large problems of simulation versus reconstruction. But there are fundamental structural issues here. The first one is on the left is quite sparse because the galaxies and all these things looks like large, but in the space of universe is very sparse and small. On the right-hand side, you can see our methodology of trying to inference is usually doing its randomized path. It's very inefficient as well. We can illustrate the methodology, how they get there. The standard diffusion model, you can see they're trying to denoise and they use the stochastic differential equation. So that steps, it could go thousands of steps. And that is a random walk in this structure. So this is where fine-grained details in the cosmic web requires this model doing very teeny steps in order to find the computation expensive. If we switch our approach to optimize this transport, we can find a solution in the wavelet space using flow matching. So what the idea here is that despite we want to do this, we try to look at the velocity field and use that as a Gaussian pair. In that case, our model is really learned by velocity field and then go straight line and avoid of the random path generation. So this optimization geometry allows us to have this solver significantly take the large steps without losing the resolution. So here, combined together with the idea, we come up with the Cosmo3DFlow, which is in essence summarize all this practice to address the other issues. So we first have our density matter input and as observable data. And then we can use this Cosmo3DFlow to train the model. And then we generate reconstruct by inference. So this solves the high dimensionality and sparsity in simulation simultaneously. In the same time, because we use physical informed Fourier transformation, so we can do it with much more precision interpretability. Dive into the details, you can see that we have a unified pipeline. On the left-hand side, we have the input, basically using the decomposition in the spatial space. And within there, we use a Fourier transformation to map to the wavelet domain. And in there, you can see on the right-hand side bottom, you have a same kind of a partition, but there's a fundamental difference is that the whole low frequency structure is concentrated, and because it's very slow in change. And the high frequency, usually is noise and other details, will be captured. And we use the ODE solver, of course, in this case. So this is forward, this training, and backward will do inference. And it's much more improved than the baseline diffusion models. To go to the details, the physics informed, which is essential here, with the solver is that we have a time from 0 to 1, and you can see we embedded the Fourier transformation with that factor 2 downsampling. So they're going through this 3D unit. I want to point it out here is that what the loss function we're really training for is the learning part. The model is really learning the velocity field regression. So you can see we're starting from the noise, and then we get to the initial condition, and we train these models. On the other hand, the power spectrum says that we can incorporate that loss into these functions, combine them, and constrain by regulation so that we have a very small 0.01 so that we can contain it to not go to very large losses. With all this combined, I wanted to clarify a little bit of the difference of fundamental simulation compared to our current approach. Usually, simulation we can use statistically is the probability distribution, like Bayesian. Here, we're using frequency. It's point-based. You can see that is for the path of transport is point estimation is much more efficient. And we also have this learning deterministic, which is based on velocity. So that distinguishes itself with traditional method. Let's look at the result. First, let's look at the fidelity quality. If we have preserving the cosmic web, one major challenge is to look at the small scale structures, and might be very important. And on the right-hand side, you can see a model can capture the small structure. On the left-hand side, was the diffusion model is look pretty missed out the small structures. if we have a multiple data set, we use in the cohorted data set, and you can see that in each of this case, we compare these two baseline versus what we're doing here, the error rate, you can see it's much lower using Cosmo3DFlow method. And I wanted to zoom in into a little bit of detail to explain the robustness of this method. Because cross-correlation you show in here is that from left-hand side is a low resolution, 32 by 32 by 32. On the right-hand side, go up to 128. So you can see that at the high resolution, both models worked reasonably well. But when the lower resolution, apparently that the wavelet flow model is much better. And some of the model method is using that train and a low resolution and then tune and high resolution for inference. But this gives you the option. You can train and lower or higher resolution without losing accuracy. Finally, we want to validate our physics. And we can compare side by side what it implies. So we can see we have almost in power spectrum cross-correlation transfer function, we can see almost close to perfect alignment in the result. Finally, the challenge still remains. And in this case, we can see that if you increase the resolution from 32 up to 128, it dramatically increasing the GPU memory usage. And the blue bar is our method, and the white bar is the diffusion-based models. You can see that the key barrier is that it go up to 15 gigabytes. In the cloud space, we have another inference structure is that if you use lambda function using AWS for a very cost-effective way, they only have 10 gigabytes of memory space. And if you go up to 256, even to 512, beyond the size of the memory requirements, beyond in single node of GPU computer. On the other hand, the time, this is a log scale chart. You can see that in 128, our model tested is 5 seconds, and the diffusion model is 4 minutes. So this gap will continue to go up with increasing the size of the n squared, that kind of a computation implications. I want to give you a very short demo to show these two methods, how fast they can converge. And you can see that the yellow is our method, it's already converged because it's a factor of 10 less steps. And now the diffusion model is closing the gap. So there's a factor of 10 difference in this convergence and the error rate. And error rate, you can see that we have very low errors in diffusion models, high error rate in the diffusion model, and ours is relatively small and relatively constant and robust. To summarize, we have the speed, acceleration, a factor of 50 times at the resolution of 128. So you can imagine that will increase even more drastically when we have the resolution higher, especially the Vera Rubin and other telescopes coming online and produce the images. So I want to conclude with all my talk and want to especially thank my collaborators within the Institute, including Arias Group, including my students. We come to this stage by learning a lot from you and made a lot of errors, but finally we find some way that we hope we can improve the computation efficiency. I want to go back to the origin of this whole project, Cosmic AI. This really is enabled to make the scientists, especially astronomers, be able to tackle their challenging questions much easier But we have a gap here. We have the physical world, observable data. We have the simulation, theoretical things. We want to bridge this gap. That concludes with my envision in the future. In the very near future, is we want to bridge it with use the model we created and fit it into the observable data. By doing that, we can reconstruct the universe in the virtual world. That closed group of the future, I think, is very exciting time for digital twin, with actually human is in the centerpiece, interact with both worlds. I thank you for the talk, and if you have any questions, please feel free to ask.